This is the second video for the Chapter 7 notes. Section 7.2 is estimating a population mean. So 7.1 was dealing with proportions and 7.2 is dealing with means. So it says, remember, x bar is the point estimate of mu. We can use a z statistic to determine the probability of getting a certain sample mean if the sample is significantly large, greater than or equal to 30. If the sample is small, then the distribution is not normally distributed and a t-distribution must be used instead of a z statistic. A t-distribution is more spread out than a z-distribution. So you can see in the picture here that we have three different graphs, and one of them is going to be the z, our standard normal distribution, and one is our t distribution when n is close to 30, and then you can see when n is really small, less than 30, then our t distribution is more spread out. But the closer that t gets to being infinitely large or greater than or equal to 30, it gets more to looking like that z distribution. The t-distribution is typically used to study the mean of a population rather than to study the individuals within a population. In particular, it is used in many cases when you use data to estimate the population mean. For example, using a sample mean of 200 homes to estimate the average price of all new homes in California. The connection between the normal distribution and the t-distribution is that the t-distribution is often used for analyzing the mean of a population if the population has a normal distribution or fairly close to it. Its role is especially important if your data set is small or if you don't know the standard deviation of the population, which is often the case. So we have a student t-distribution. So suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t equals x bar minus mu over our standard deviation divided by the square root of n, which is our sample size, follows a student's t-distribution with n minus 1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. Right below this we have some properties of our student t-distribution. First one says the t-distribution is different for different degrees of freedom. 2, the t-distribution is centered at 0 and is symmetric to 0. 3 says the area under the curve is 1. The area under the curve to the right of 0 is equal to the area under the curve and to the left of 0, which equals 0.5. As t increases and decreases without bounds, the graph approaches but never equals 0. And 5 says the area in the tails of the t-distribution is a little greater than the area in the tails of a standard normal distribution. 6 says as the sample size n increases, the density curve of t gets closer to the standard normal density curve, and this is called the law of large numbers. So very similar properties to what we had seen in our normal distribution. So at the top of the next page, it says, remember that z sub alpha is used to represent a z-score with an area under the normal curve and to the right of z sub alpha is equal to alpha, and again to the right. And it says similarly, t sub alpha is used to represent the t-value where an area under the t-distribution and to the right of t sub alpha is alpha. So underneath this, we do have a little box that tells us about using the graphing calculator. I do want to point out that this is only for a TI-84 graphing calculator, so definitely something you want to make sure your calculator has on it. If you have a TI-83, you have a couple options to get this program onto your calculator. One is going to be to take your TI-83 to our Mark Center, and they will upload the programs that you are missing onto it quickly. It takes about a minute. Or you can also program them yourselves, and you can email me if you need a video to do that on your own. But this is using a TI-84 graphing calculator, and we are finding a t-value. So we're going to go second vars, find inverse t, INVT, and it says note, use inverse norm if sigma is known, and so that would be our case if we do know the population standard deviation. And using this, we're going to type in area to the left and degrees of freedom. And again, degrees of freedom is n minus 1. And so for this, we have an example right below. that says determine the following and round through decimal places. Part A says find the t-value such that the area in the right tail is 0.02 with 19 degrees of freedom. So this is in our right tail. And so I'm going to go ahead and draw a picture. Remember, your t distribution is very similar to your standard normal distribution. However, it is a little bit wider. And so I'm going to put a t-value here. If you notice, that right tail is going to be really small. So I'm going to put a line over here. This is 0.02. I'm going to call my value down here t. That means the area total under the curve is 1, so that area to the left of t is going to be 0.98. And so in order to find our t value, we are going to use inverse t. We do not know our population standard deviation, so I am not going to use inverse norm. Area to the left is 0.98, and then 19 degrees of freedom are given to us. On the graphing calculator, we're going to go to second vars, and then go to inverse t, INVT, and area to the left is 0.98, comma, degrees of freedom is 19. Close your parentheses and select enter. So from our graphing calculator, we get a value of 2.205. Part B says find the t-value such that the area to the right tail is 0.10 with 32 degrees of freedom. So again, sketching our curve. A little bit larger of an area here. So this time in the right tail it's 0.10. That means area to the left is going to be 0.90 because that total area under the curve is equal to 1. So our t-value is going to be found by using inverse of t, area to the left, which is 0.90, and comma 32, since those are our degrees of freedom. On the graphing calculator, we're going to go to second vars, inverse t, area to the left is 0.90, comma, degrees of freedom is 32. Close your parentheses, select enter, and then round 3 decimal places. From the graphing calculator, we get a value of 1.309. Part C says find the t-value such that the area to the left of the t-value is 0.05 with 6 degrees of freedom. So again, sketching our curve, and this time our area to the left is small, so I'm going to go ahead and put my t-value on the left. This is 0.05, and so in order to find our t-value, we are going to use inverse t. Area to the left we do have, which is 0.05, comma, our degrees of freedom, which were also given to us, which are 6. On the graphing calculator, we're going to go second vars, inverse t, area to the left is 0.05, comma, 6 degrees of freedom. Close your parentheses and select enter. From the graphing calculator, we get a t-value of negative 1.943. Part D says find the critical values that are corresponding to a 95% confidence. Assume 16 degrees of freedom. So again, taking the time to sketch our curve to get a better understanding of what's going on in this case. And anytime that we're dealing with a 95% confidence or any type of confidence, remember that we are going to have 2 cutoff values. And so this is going to be 95% confidence. I'm going to go ahead and call this one T sub 1 and this one T sub 2. And since the total area under the curve is 1, if I subtract that, I get 0.05. And then if I divide that by 2, I get that each tail is going to have 0.025. So in order to find T sub 1, we are going to use inverse T. Area to the left we have is 0.025, comma, 16 degrees of freedom. And then in order to find T sub 2, we're going to use inverse T. Area to the left, you have to add up everything. So we have 0.95 plus 0.025. That's all to the left, and we get 0.975. Again, 16 degrees of freedom. On the graphing calculator, we're going to go second vars, inverse T, Area to the left is 0.025 and 16 degrees of freedom. Select enter. That's our first value. Our second one, we're going to do the same exact thing. So second vars, inverse t. Area to the left this time is 0.975 and 16 degrees of freedom. Close your parentheses and select enter. From the graphing calculator, we get negative 2.120 and positive 2.120. Right below this, we have a box that talks about constructing a confidence interval for a population mean with a TI 83 and 84 calculator. So step one is going to be to verify that we can actually conduct this and find our confidence interval, which would be verifying that it's a simple random sample and that our population is normally distributed or our sample is greater than or equal to 30. Step two says to go to stat, test, and then t interval. There is a note here that does say choose z interval if sigma is known. This is not too common of a case that we have. We're mostly going to be using t interval. If the data is raw, you're going to highlight data. You input your data into L1 and then set the list to L1 and frequency to 1. If summary statistics are known, then you're going to highlight stats and enter in all the statistics. Enter the confidence level followed by the C level and highlight calculate, press enter, and then it's going to give you the lower limit and the upper limit. And then the big thing here is to make sure that you enter the two small boxes to the left of the calculator steps show what you would have to enter in, and the numbers will be different for data or for stats, and this just depends on the problem and the numbers and the values that you are given. So at the top of the next page we have an example that says the summary stats for a randomly selected weight of a newborn girl is, and they give us N, X bar, and S. It says the confidence level is 95%, round 3 decimal places. Part A says find either the critical value T sub alpha over 2 or the critical value Z alpha over 2, whichever is appropriate. So we do not know sigma. Sigma is our population standard deviation, so this is unknown. And so since we don't know it, we are going to use T sub alpha over 2. And so let's go ahead and sketch a little graph of our t distribution. And since we're dealing with a 95% confidence, remember that we're going to have two tails, so that means 95 is going to be in the middle. And that means that in each of those tails, we are going to have 0.025. That total area needs to be 1 that's underneath that curve. So in order to find our t sub alpha over 2 value that we have, this is going to be inverse t. Area to the left, our critical values are going to be the positive ones. So I'm going to call this one t sub alpha over 2. Area to the left is going to be 0.975, comma, and then degrees of freedom. Degrees of freedom, and they abbreviate this df, is n minus 1. So our degrees of freedom is going to be 205 minus 1, which is 204. And so that's our degrees of freedom. On the graphing calculator, we're going to go second vars, inverse t. Area to the left is 0.975 and 204 degrees of freedom. Close your parentheses, select enter. From the graphing calculator, we get a value of 1.972. Part B says to construct a confidence interval estimate of the mean. And so since we do not know sigma, we are going to be using t interval. On the graphing calculator, we're going to select our statistics button, or stat. From here, scroll right to test. And from here, you need to select t interval. X bar is given as 30.4. Our sample standard deviation S is given as 7.1. N is 205, and our C level is 0.95 or 95. From here, select enter, and it's going to give you the lower bound and the upper bound. So from our graphing calculator, we get our lower bound is 29.422, and our upper bound is 31.378. Remember that you do need to interpret your confidence intervals, and so we're going to say about 95% of these confidence intervals will contain the true population mean weight of newborn girls and about 5% will not. So again, just like how we saw in the previous section, on MyOpenMath, these are values that you're going to be entering in on MyOpenMath. And then whenever you need to write this on your own, you can get those values. 95 is coming from our confidence interval that we're dealing with, and then the 5% is again 100% minus 95. But you also need to make sure that you do discuss exactly what it is that this problem is talking about, which is the weights of newborn baby girls. The example right below says travelers pay taxes for flying car rentals and hotels. The following data represents the total travel tax for a 3-day business trip in 8 randomly selected cities, round 3 decimal places. So we're given a list of numbers. Part A says determine the best point estimate for the population mean travel tax. That means we're going to have to calculate X bar. So in order to do this, we need to take the time to put in all of our numbers into L1 and do 1var stats. On the graphing calculator, to get X bar, which is our point estimate, we need to first go to Stat, select Edit, and in L1, you need to make sure that you have all of those values typed. Double check to make sure they're typed correctly. Then we're going to select Stat again, go to Calc, go to 1var stats, and then select Enter. From here, we're going to get X bar, which is 83.349 when you round 3 decimal places. From the graphing calculator, we get 83.349. Part B says to construct and interpret a 95% confidence interval to estimate the mean tax paid for the 3-day business trip. So we do not know our population standard deviation. I know you can find the sample standard deviation on your calculator, but population would be for all cities, and we do not have that. So we are going to be using t-interval, and this time we have to go to data. On the graphing calculator, we're going to go to stat, test, t-interval, and for this one we have data. And since we typed all of our numbers in L1, that's where my list is. Frequency is set to 1. And you'll notice you do actually get X bar using t-interval also. And this does match to what you had in part A. And then you get your, from the graphing calculator, we know that that mean is going to be in between those two values. Our lower bound is going to be 73.046, says dollars. And our upper bound is going to be 93.652. So again, we do need to interpret our confidence intervals. And so interpreting our confidence intervals, we're going to say about 95% of these confidence intervals will contain the true. And again, make sure to talk about what it is that we're dealing with, which is population, mean travel tax for a 3-day trip, and about 5% will not. Again, we are dealing with the 95% up here because that is our confidence, and 5% is that leftover part. And then we also need to discuss what it is that we are dealing with for this problem, which is the mean travel tax for a 3-day business trip. Part C says, what would you recommend to a researcher who wants to increase the precision of the interval but does not have access to any additional data? So we can decrease the level of confidence. Right below it says, what could be done to increase the precision of a confidence interval? And so we have a couple things listed here. One is going to be to increase the sample size or decrease the level of confidence like we saw previously in part C. On the next page, we have some more formulas. This is for sample size needed to estimate the population mean. So the required sample size to estimate the population mean, mu, is given by, and you'll notice that we have an N formula here. The N formula is going to be Z alpha over 2 times sigma divided by E all squared. And again, remember, the Z alpha over 2 is on page 2 of chapter 7 notes. So we had 3 of them listed there that were the most commonly used, and then the example underneath did show how to get Z alpha over 2 for any value. And then it says where N is rounded up to the nearest whole integer. So we have an example right below that says, in a recent Gallup poll asked Americans to disclose the number of books that they read during the previous year. Initial survey results indicate that sigma is equal to 16.6 books. So part A says how many subjects are needed to estimate the number of books Americans read the previous year within 4 books at a 95% confidence. So a lot of numbers and ideas going through this. First of all, this is a means problem. The reason why is because we're talking about the number of books that people read. This is not a proportion. This is talking about like an average. So an average, again, would be a mean. And it is asking for how many subjects in part A, which means we are looking for N. So writing our formula that is up above, we have Z sub alpha over 2 times sigma divided by E all squared. And so from here, E is our margin of error, and it does say within 4 books. So we do know that E is equal to 4. And we do know that sigma is equal to 16.6. So we do need to get that Z sub alpha over 2. And remember that corresponds with our confidence level. And for this one, we are 95% confident. At our table, when we are 95% confident, our Z value, our critical value, is going to be 1.960. So from page 2, we know that Z sub alpha over 2 is 1.960. Sigma is 16.6. E is equal to 4. And we're going to square that entire expression. From here, we're going to plug this all into our calculator, and we get 66.16. But remember, we're always going to round up when we're determining our sample size. And so this is going to be 67 people or subjects. Part B says how many subjects are needed to estimate the mean number of books that Americans read the previous year within 2 books with a 95% confidence. So this one we're still 95% confident, but it does say within 2 books. So that would be our margin of error this time is equal to 2. So N is equal to, using that same formula, and then we're going to go ahead and we have the same Z sub alpha over 2 value since our confidence did not change, so that's 1.960. Standard deviation is still 16.6, but this time E is equal to 2. And squaring that whole entire expression, we plug this into our calculator and get 264.65. And for this, we are going to round up with sample size. And so we get 265 people that we would have to survey. Part C says how many subjects are needed to estimate the number of books that Americans read the previous year within 4 books at a 99% confidence. So now our confidence is increasing and E is back to 4 books. So E is equal to 4 again. And then it also says compare your result to part A. So we'll look at that rest of the question in just a moment. Again, I'm going to copy down the formula that I have, which is N equals, and it's Z sub alpha over 2 times sigma over E squared. And so we're going to have to go back to page 2 to get the Z sub alpha over 2 value that we need, that critical value. When we are 99% confident, our Z alpha over 2 value is going to be 2.576. So from the table on page 2, we know that Z sub alpha over 2 is 2.576. Sigma is still 16.6. And our margin of error is 4. Squaring this, we get 114.28. And again, we do need to round up. Rounding up, we do get 115 people. So the other part of this question says to compare results to part A. How does increasing the level of confidence in the estimate affect the sample size? Why is this reasonable? So we went from being in part A, being 95% confident, and we needed to survey 67 people. Still the same margin of error was still 4 for that one, along with part C. Part C, the difference is that our confidence increased, and in order to have an increased confidence, we had to survey more people. So when I would feel more confident if we had a survey done of more people, and that's usually typically the case. So when increasing the level of confidence from 95% to 99%, we increased our sample size. I feel more confident with a larger number of people being studied. So this concludes our Chapter 7 notes.